Hello everyone, welcome back to Algebra. Today we're going to be talking about the class equation. So the class equation is a consequence of group actions. So let me just give you an example of a class equation to fix ideas. So here's my example. We're going to take x to be 1, 2, 3, 4, 5, 6, and 7. And G is going to be the group acting on x. And the group G is going to be the identity and the permutation 1, 2, 3, 4, 5, 6, and 3, 5, 4, 6, and 1, 2, 3, 6, 5, 4. Then let's look at orbits. So the orbit of 1, we've seen before, I think, this example. 1 is being sent to 1, 1 is sent to 2, 1 is stable, and 1 is sent to 2. So the orbit of 1 is 1, 2. And then you see that the orbit of 2 is 2, 1. So it's the same orbit. What about the orbit of 3? You can see that 3 is stable. 3 can go to 4. And then 3 can go to 5, and 3 can go to 6. So 3 can go anywhere from 3, you can go to 4, to 5, or to 6. Not to 1 and 2, though, but you can go to 3, 4, 5, or 6. And then that also tells me that the orbit of 4 and the orbit of 5 and the orbit of 6 are all the same. Great. What about the orbit of 7? 7 is not touched by any of those permutations, so 7 is a singleton. So 7 just goes to itself. Okay. So the class equation is actually comes from the fact that the orbits, which remember we define G equivalents, the orbits are the equivalence classes under these G equivalents. And we know that when you have an equivalence relation, you can break your set into disjoint equivalence classes. Well, the same thing happens here. I have the orbit of 1 union, the orbit of 3 union, the orbit of 7 gives me a disjoint union of x into subsets 1, 2, 3, 4, 5, and 6, and 7. And the class equation is going to tell me about something about the sizes of x. So the size of x will be the size of this orbit plus the size of this orbit plus the size of this orbit. So it just says that 7 is 1 plus, oh, I'm sorry, there are two elements in here. There are 2 plus 4 plus 1. Okay. And one more thing to notice is that this one has one element, that one has one element. So one element, and then we say that this is a fixed point by the action. And the fixed points are going to be part of the equation. There's those that are fixed points. Those are orbits that have exactly one element. And those here, they have more than one element. We are going to call the non-trivial orbits. Okay, so now let's see what the class equation, or what this equation, what it reads like in general. So in general, let X be a finite G set, and first of all, so we're going to talk about the orbits. So we're going to talk about the orbits of order 1, the orbits that exactly have one element. Those are the elements that are in what we call the fixed points in X. So those fixed points we're going to call X sub G. Sometimes you'll see fixed by G in X. So those are those elements in X that are fixed by every single element of G. Whoops. When I act on X, I get X back for all G in G. So we have those, and we are going to write OX1 through OXN for the non-trivial orbits. So each one of those orbits is of size at least 2. And x1 through xn are representatives of the orders of the orbits. So for example, here we had a representative for this orbit, it was 1, but I could have picked 2 as a representative, or here I've picked 3, but I could have picked 4, 5, or 6. And this orbit is one of those that has only one element in it. So in here, the fixed points are exactly, it's just 7 itself. Okay, then because we know that X will be partitioned into orbits, into all the orbits, we will have that X is xg union, in this case, the union of each orbit up to xn. Is this joint union of all these orbits, and therefore the size of X is the size of the however many fixed points we have, plus the size of the non-trivial orbits. Okay, so this seems, so again, where x1 through xn are representatives of the non-trivial orbits on X. Okay, so this equation, this seemingly harmless equation, is actually very important and has a lot of applications. And the reason is that we've transformed something about group theory into a question of integers. Now we have an equation in natural numbers that these natural numbers is equal to the sum of these natural numbers. And what we're going to do, once we do that, we can use number theory and actually do things about like divisibility conditions on these to say something about the divisibility of the set, of the size of the set X. And that's going to have some pretty amazing consequences. So let's do one special case, which is sometimes was actually called the class equation, is this special case of the action of G acting on G via conjugation. So let's see what happens if I do that. Now let X be G, and G is acting on G via conjugation. Then, first of all, the orbit of X is, well, it is all the elements G times X as G runs over every G. But the action here is conjugation, so it's Gx G inverse for every G in G. And this is called the conjugacy class of X in G. Okay, what are the fixed points? So what I would call, we call X sub G. So in this case, it's really G sub G. The fixed points in G with the action via conjugation of G. So those are points in X, which are elements of the group, such that H dot G is G for all H in G, which the action here is conjugation. So it's those G's such that whenever I conjugate, I get G for every H in G. But that is, if I move, if I multiply on the right by H, those are those G's such that HG is GH for every H in G. So there are elements in G that commute with every single element in G. We have a name for that, that is called the center of our group. This is the center of G, and that is a group. Okay, it's a subgroup of G. All right, so we have identified what is the set of fixed points, and then the non-trivial orbits are non-trivial conjugacy classes. Non-trivial orbits correspond to the non-trivial conjugacy classes. And then what we get is, well, we get the class equation. So remember, we had x is the size of the fixed points plus the sum of the disjoint non-trivial classes or orbits. So in our case, what we get is x is g, so the size of the group is the size of the center, because the center we said is the fixed points under the action, plus the sizes of all the non-trivial conjugacy classes. So what we get is the size of the group, the order of the group is equal to the size of the center plus the sum of the orders of non-trivial conjugacy classes. We're going to simplify this formula even more, or replace this using the fact that we've proved the orbit stabilizer theorem. Remember that we proved that the size of the orbit is the index of the stabilizer. So we're going to use that to replace this by certain indices. But let's do some examples of, at least one example of this business of this class equation in terms of conjugacy classes for a particular group. So we're going to do this for S3. So here is an example of this. We're going to take G is S3, and it's going to act on S3 itself via conjugation. And then we have, there's three classes. There is a class of the identity. The identity under conjugation, it is always the identity. If I conjugate by anything in S3, I will get just G inverse, and I get the identity back. So there's only one class. There is another class. So by the way, this is the only class of exactly one element, because that is the center. So this is the center of S3, is only the identity. And then for non-trivial classes, I have one class with 1, 2, 3, and 1, 3, 2, because, well, 1, 2, 1, 2, 3, 1, 2 inverse, you can check that that is 1, 3, 2, and 1, 3, 1, 2, 3, 1, 3 inverse is 1, 2, 3. So these are conjugates. And if you do any other conjugation, you get back one of these two. So it's another class. And then there is one more class, which is 1, 2, 1, 3, and 2, 3. That's another conjugacy class with three elements. So what the class equation in this case tells me is that the size of the group is the size of the center plus the size of orbits, of these joint orbits. And in this case, it's telling me that 6 is equal to 1 plus, and then 2 plus 3. So that 6 is 1 plus 2 plus 3. That's all it tells me. So again, it seems harmless. It seems like we are just moving around symbols and notation, but we're going to see that thanks to this, we're going to be able to prove some significant results. So now, one more example I can do is a little bit more abstract, is that, so let G be an abelian group, be finite abelian. Then we know then that the center, everything commutes with everything. The center is all of G. So now every orbit is exactly one element. So for every orbit, those Gx, G inverse, as we run through G's in G's, all of those, because it commutes, is just X. So this is just X. So that means then that the class equation just reads G is the size of the center plus nothing else. there is no orbits, so there's just a 0 here, so it's just this size of the center. Okay, so in that case, every orbit is exactly the orbit of one element, or if you want, you can write it. G is the sum of um, uh, disjoint orbits, but every orbit has exactly one element. So that's how it reads. Okay, so now let me go back to the equation, to the class equation, and replace, as I said, the sizes of the orbits by a certain index. So now let's go back to the case of G acting on G via conjugation. And then we had that G is the size of the center, which is the fixed points, plus the size of non-trivial conjugacy classes. And recall that we have proved the orbit stabilizer theorem. So the orbit of X is the size of the index. It's the index of the stabilizer in G. By the way, first remark is that the index is the size of G divided by the size of the stabilizer, and this is a divisor of the size of G. Therefore, the size of an orbit divides the order of the group. Okay, so that's important. And second, the stabilizer in this case, when we're talking about, or the stabilizer is always those G's that stabilize X, that send X to itself. But in here, we're talking about conjugation. So those elements G, such that Gx, G inverse is X itself. And there is a name for that, those elements that conjugate X to itself. That is called the centralizer of X. So this is called the centralizer. The centralizer of X in G. And it is a subgroup. We have proved that the stabilizer is a subgroup, so this is a subgroup also. And if we go back to our class equation, then we're going to be able to replace the size of orbits with the index of the centralizer. So the size of X, the size of G will be the size of the center plus the size of the centralizer of, or the indices of the centralizers of representatives of non-trivial conjugacy classes, like that. And this is sometimes authors, this is exactly what they refer to as the class equation. But many times myself and some other people just do anything that is X is equal to the fixed points under G of X plus the sum of non-trivial orbits. I also call this a class equation because with different actions, this is still true and it can be still very useful. By the way, notice that when I said that the size of the orbits divide the order of the group, let's see that in the example that we saw before, that with S3 acting on S3 via conjugation, there were 3 orbits, where there was the size of the, there are orbits of order 1, those of course divide the order of the group, but actually the order of the center, because it is a subgroup, it also divides the order of S3. In this case, the center is just of order 1. But then we have the size of the orbit of 1, 2, 3. And that orbit, we saw that it was 1, 2, 3, and 1, 3, 2. It has size 2, which also divides the order of S3. So this says that 1 divides 6. This says that 2 divides 6. and then the orbit of 1, 2 was 1, 2, 2, 3, and 1, 3 has size 3, which is also a divisor of H3. So we get three different types of orbits, and all the orders divide the size of the orbits divide the order of the group. Okay, let me give you one last example of class equations. So here is one more example. Let G be D4 acting on D4 via conjugation. So remember that D4 is given by R and S, such that R to the 4 is 1 and S squared is 1. And then we also have that SRS is R inverse. You can also realize D4 as a subgroup in S4. So I'm going to write it like that so it's easier to see orbits and so on. So it is given by these permutations of the vertices 1, 2, 3, 4, 1, 4, 3, 2, 1, 3, 2, 4, and 1, 2, 3, 4, and 1, 4, 2, 3. This is D4 as a subgroup of S4. Okay, so what is the center of D4? In the center in D4, there is two elements in the center. There is 1, but also R squared is an element that is in the center. Now, what is R squared? R squared this is R, this is an element of order 4, and if I square it, I get this. So R squared is 1 and 1, 3, 2, 4. It turns out that these two elements are in the center. Then via conjugation, there is the following orbits. So 1, 3 turns out to be conjugate to 2, 4 via the conjugation that 1, 2, 3, 4, 1, 2, 1, 1, 1, 3. And the inverse of 1, 2, 3, 4 is 1, 4, 3, 2. It turns out I get 2, 4. So those are conjugates, and those are the only elements that are conjugate to 1, 3. Then there is another class, which is the one of 1, 2, 3, 4 conjugates to 1, 4, 3, 2. Notice that the order of a conjugate has to be equal to the element itself. So the conjugates of 1, 2, 3, 4 have to be also elements of order 4. And if you go through this list, the only elements of order 4 are 1, 2, 3, 4, and 1, 4, 3, 2. So if there is a conjugate to 1, 2, 3, 4, it can only be this one. Similarly, for 1, 3, 1, 3 has to be the conjugate to other elements of order 2. And you can see that actually this cannot be conjugate to a product of two disjoint cycles. So in any case, it cannot be conjugate to this one. So it has to be this. So you can get clues of what can be conjugate, and then you can prove that these are the only conjugates. And we are left with one other class, 1, 2, 3, 4, and 1, 4, 2, 3 are conjugate elements. So there is the center, and then the orbit of 1, 3, and then the orbit of 1, 2, 3, 4, and the orbit of 1, 2, 3, 4 are the disjoint orbits, the disjoint non-trivial orbits. And the class equation reads that D4 is, which is of size 8, is 2, the size of the center, plus 2, the orbit of 1, 3, plus 2, the orbit of 1, 2, 3, 4, plus 2, the orbit of 1, 2, 3, 4. So I will write that in here. This corresponds to this. This corresponds to the orbit of 1, 3. This corresponds to the orbit of 1, 2, 3, 4. And this corresponds to the orbit of 1, 2, 3, 4. So that's what the class equation. So this is the class equation for D4. And next, we're actually going to use the class equation to prove some interesting results. So that we will do in the next video.